Hello. In this video today we're having a look at the introduction to angular mechanics. In order to do this we come across three new Greek letters and these represent the translational equivalents of distance and velocity and acceleration. So we'll start at the beginning here. If we've got an object, a fixed object, something solid like a coin, and we've got point A on the circumference of the coin, and we move point A through to a second point, and it travels a distance r, where r represents the radius of the circle, then we say that this object has been transformed through an angle of exactly 1 radian. So I find it helpful to think of about 6 radians in a circle, and so if we move through a sixth of a circle, then that's called a radian. Now, if we have something that turns through a different number of degrees, we simply work out how much of a circle this is, we multiply it by 2 pi, and then we can convert that again into radians. If it has 3 rotations, then that would just be 3 times 2 pi, so that would give you your 6 pi radians. Now bear in mind that radian is not an actual unit, it's just a measure of proportionality. Now if we have a look at this object, point A and point B, then point B, when it travels around to this point, will travel a lesser distance than point A will. There's no point on an object like this where they can overtake each other in an angular sense. So what we have now is we're now rotating this object through 3.14 radians, which is half a rotation, or 180 degrees. Now in this case, point A and point B will have identical angular displacement because they've been turned through the same angle. So even though point A has to travel further than B, their angular displacement is identical. Now in the box over here, what we've got is the distance something travels is equal to the radius multiplied by the number of radians it's turned through. So that's simply your circumference of a circle. And then with rearrangement going the other way, if you're trying to work out what the angular displacement is and you have a distance traveled around a circle, you can just simply divide it by the radius. And so here we've got an example. You've got a 2 meter radius disk, and then an object moves 1 meter around the circumference. So as it does so, it travels through half a radian. Okay, so here they are. That's our 180 degrees there. Okay. Now, the next concept we come to has this symbol here. So this is omega. Theta is the one that you've used for angles, and we're using that for angular displacement, but in radians rather than degrees. And then lowercase omega, this tells you how fast an object is spinning. So what we have now here is object A is twice as far out from the center as B, therefore this is its instantaneous velocity vector and it's twice as large. So there's this directly proportional relationship between any point on a circle and its velocity when it rotates. So what we have now is to calculate tangential velocity, it's simply distance divided by time. There's the distance on the circle. Increasing the radius will decrease the distance in the same amount of time, therefore we end up with this proportionality. So the velocity is directly proportional to the radius for an object that is rotating at the same rate. Also, by rearrangement, if you're trying to calculate the angular velocity, it's simply the linear velocity divided by radius. So the same pattern as we saw for angular displacement and dividing the linear distance by the radius. So as they rotate through 2 cycles. Right, so that was an angular displacement of -2 cycles, which is -6 pi radians, and it happened in around about 6 seconds. So that would be 1 radian per second. Okay, now this you might want to pause the video at this stage. What we have here is a sample question. This is the sort of thing that NCEA would look at, and it's just making use of the concepts that we've covered so far in this part of the video. Alright, I'll just reveal the answers now. So have a go at it first. Don't just like have a look at the answers and then go, yep, that was nice and straightforward. Try it first. So as it travels through there's our 2 rotations for a bicycle wheel. And then down here, you can check your answers. And if you have any issues, you can just let me know if you're getting something different. Okay, finally, what we're looking for here is angular acceleration. So in this case, instead of normal acceleration being change in velocity over time, this is change in angular velocity over change in time. And the units you can see here, radians per second. Again, not a true unit. Now, what we can say here is that in this example, if you watch this rotation, we've got acceleration. It starts off very slowly, and then it increases its speed of rotation. So in this case here, we've got acceleration is alpha times r, or angular acceleration is the ratio of linear acceleration divided by r. Once more, simple template question. And the answers. And then finally our summary. Alright, thank you for watching. I hope it's been helpful to you.